So our next speaker is Stefan Vöth.
Yeah, thank you for being here. We advance with some German English, and I want to continue with my topic of last year about buffers. Last year I had a look on hydraulic buffers in lifts, and I spoke about their calculation and outcome according to EN 8120. And afterwards, I was asking myself whether these calculations are the end of the circumstances under which the buffers may work. Probably they never work, but okay. We hope, and but anyway, I consider. This is the agenda, and yes, the main point is that I asked myself what may be unfavorable conditions for this operation of the buffers. We will look on in the following. Basically, you can give me a lot of hints because I'm from crane business. So I'm not aware about the details of lifts, and maybe I can learn something from you. But you see, basically the functionality of the buffers is more or less the same. Sometimes even at cranes you have some driving forces like at lift applications. To repeat from last year, what is the basic functionality? You have some oil, you press it through a throttle, and the target is to decelerate your load. And the target is to have some more or less constant deceleration, which means a constant force acting onto the lift car. You have the choice, the work you have to do, to create it by higher forces combined with smaller strokes, or smaller forces with higher strokes. And the standard will help you looking on this because a minimum stroke is required. You can calculate it by this standard. And as I already learned, this is a so-called jump height in English. Yeah? But this is not the only requirement. There are further requirements. The second is an average deceleration less than g at this impact speed, and a maximum time span of 40 milliseconds for accelerations higher than 2.5 g. And all these requirements have to be met. For me, maybe there's the question in which cases they have to be met. But maybe you don't know. For me, the question occurs, what are unfavorable conditions? And some risk will realize. Yeah? And one risk may be that your speed governor will act, and maybe the speed occurring during this process will be the impact speed for your damper. Analyzing the standard, you can calculate the speed at which your speed governor has to act, and you get some trigger speeds you can see on the left-hand side. For faster lift, this more or less means 1.25, the nominal speed, is the triggering speed of the speed limiter. For smaller lifts, it's even more. Following, I consider exactly the two lift configurations from last year. Smaller lift at smaller speed, and a larger lift at higher speed of 4 meters per second. And for this, I analyzed with my calculation program, what happens during impact. And these are more or less the results. So you see a bundle of graphs like this now. The first situation is the lift at 1 meters per second. And just to explain it once, this is the buffer force at the backstroke, the speed during buffering process, the red, the deceleration, blue, the energy absorbed by the buffer, and yellow, you can see the time lapsing during this process. And if you look at the first case with the lift with maximum mass, at rated speed, all the requirements are met. No problem. This is what you can wait. And if you go to the minimum mass of this lift, then also the average deceleration is met. You get quite higher decelerations, 16G. But these higher decelerations, they act for a very small time, 10 milliseconds only. So this is no problem looking on this situation. But now I take this lift, considering the situation that the speed governor is acting. We have already some higher speed. And looking on such a situation, you see the decelerations even get higher. You get very high peaks of buffer forces in the beginning, this blue one, and according decelerations, but they act for a very short time. So you can say, okay, the average deceleration is not less than 1G, but the standard only requires it for 115% speed, not this speed. And the high decelerations act very short time. Fine. So this is the second case. Our lift at 4 meters per second. At maximum mass and rated speed, the buffer should be okay, and it is okay. And this is the picture for the minimum mass. So there's less mass, and we have high forces acting due to the functionality of the buffer, and this leads to high decelerations. And what we can also see, in this case, they act for 45 milliseconds, which is more than allowed to the standard. And now, this is the same situation with minimum mass and the maximum speed, which is in this case 1.25 nominal speed. And it's not a real requirement, but for this case, but the requirement in general for less than 1G is not met anymore, average deceleration, and especially the high decelerations, very high, close to 20G, they act 48 milliseconds, so much more than maybe the target. So what was done now, as a measure to compensate, the throttle was modified. And in the first step, this modification was an increase of the throttle area, which means greater area, less resistance for fluid flow, and the idea was to reduce the buffer forces by this. This is in fact true for maximum mass at rated speed in the result. But if you look at minimum mass, this measure in fact does not help. the time of high decelerations even increases. Yeah? You can see 49 seconds. So you can say the compensation was a compensation into the wrong direction. Yeah? And this is why, in a second step, the throttle is created smaller, not larger. Yeah? And with this smaller throttle, we can gain good conditions for the maximum mass. But for the minimum mass, at the maximum speed, the picture looks like this. Yeah? Especially the high decelerations, they still occur for a long time, 44 milliseconds. But this is less time than for the original condition. So a smaller throttle is the right direction of modification. And this is why I've created an even smaller throttle. And you can see, doing this for maximum mass, everything is okay. And for minimum mass, even the condition about this time span is okay. Yeah, we can reduce the time span of decelerations above 2.45 G down to 38 milliseconds. Yeah? So this helped. The average deceleration requirement we cannot meet, because the buffer originally was created for 115% speed, and with 125 you are not able anymore to reach this target. Yeah. Okay, so we see it was possible to get this result. In this table you see a small summary of this data. Yeah, basically we were able to reduce by reduction of the throttle. Yeah, this is in fact the percentage of the throttle cross-sectional area applied. We were able finally to meet these requirements. Okay, conclusions. I don't want to repeat this. And I thought a little bit about it. For me, it would be interesting, what are your conclusions? Is this theoretical nonsense, or can we think about it? Because for me, not being in this business really, I ask myself, if you have safe systems, why do we apply 115% speed to the buffer? If you look to larger installations, this is a lot of money you put to your project. Or on the other hand, if we have some failure of systems, for example, your speed governor acts at 125%, you have then some free drop of your system. You will get to even higher speeds than this speed, and then you get even higher decelerations than I have shown to you. What is the result of the risk analysis of such a situation? And how do you get to this buffer design according to the standard? For me, it's a myth, but maybe there's the requirement to discuss, and maybe in a far future, even to modify some of these aspects. Thank you very much.
Before we open, Stefan, thank you. Before we open the floor to questions,
okay, thank you.
Before you rush off, I have a question.
You have a question.
Other people may have a question as well. The initial peak acceleration that you had, what was that? What was causing that?
Basically, this is just caused by your impact speed. Because if you have some certain buffer design, looking on the mechanics and the hydraulics of the system, just the impact speed decides on the buffer force. And then the mass of your system comes into the game, because at a certain force level, this force will induce some deceleration. It just depends on your mass. This is why the different load conditions are of interest.
Thank you for that. I'm being selfish. That was my question. Are there any questions for anyone on the floor? No? Okay. Fine. Thank you very much.
Thank you.